here is another question. This time we are asked to draw the load extension graph of the information extracted from an experiment conducted to determine the modulus of elasticity of a sample of mined steel. The mean diameter of the wire is given. So the mean diameter is given as 1.3 meters, 1.3 millimeters. We can convert that to meter. It becomes 0.0013 meters. 0.0013 meters. Okay, they're giving the length of the material. The length is 8.0 meters. We're asked to find or to determine the modulus of elasticity of the sample. So we are finding E. It's not given to us. And also we are asked to find the stress at the limit of proportionality. So the stress is not given to us. All right, now to find this or to solve this question, the first thing I do is that I have to use the formula that relates to the graph, and I know that the E is equal to the gradient or the stiffness times the original length, which is 8.0, over the area. Now to get the area, I can use the diameter. So again, it's minus t. I will use the formula area. To get my area now, is the area equal to pi d squared over 4. So I have to get my area. Then to get my stiffness, I will have to plot a graph to get my stiffness. So we have area equal to the pi times my diameter is 0.0013 meters, 0.0013 meters, or squared, divide by 4. So therefore my area becomes what? So when I put this in my calculator, pi times 0.0013 squared divided by 4, that will give us 1.327. That's 1.327 times 10 to the minus 6 meters squared. Minus 6 meters squared. So now I've gotten the area for this material. What I do next is to find the stiffness, which I say that to find the stiffness, we have to plot a graph. So I will have to plot the graph. So I come to my graph. So here is my graph. Okay. Now to plot this graph, so let me adjust my lines, because I have a lot of values, so I can adjust my lines. I can take off this part of it because I have no negative numbers. All right, good. So what I do next is to choose a scale. So I can choose a scale. Remember that okay, so what next? I choose a scale now. Let me use a dark blue marker. So let's choose a scale. Okay, step 1, here is this is my load, or call it the force. They are in Newton, and here is the extension, which is in millimeters. All right, so here's 0, Okay, on the x-axis, I will use a scale of 2 cm to 2 millimeters. So that is that here is 2, this is 4, this is 6, 8, here's 10, 12, 14, and here's 16, 18, and now we have 20 there. Then for my y-axis, in this case is the load or the force, I will use a scale of let's use 1 cm to 20 Newton. All right, so 1 cm, so 0 is 1, so here is 20, here is 40. Okay, to make my work neat, I will space it after 10 centimeters. So here is 20, here is 40, this is 60, this is 80, it should be 100, 120, here is 140, here's 160, this is 180, this is 200, this is 220, this is 240, this is 260, this is 280, this is 300. This is 320, so this is 340. I believe the last value on our table for the load is 340, so I can stop right here. All right, so now I have to plot the graph. So when the load was 0, my extension was 0, so I will mark the origin. So I have a point right here. I have a point right here. When the load was 40, this is 20, this is 40 right here. When it was 40, we have a 1.2 extension. So this is 1, this is 1, 0.2, 0.4, 0.6, 0.8, 2. So this is 0, yes, 1. This is 1, all right? This is 1. This is 1 right here. So 1.2. So go up to 4. This is 0. This is 20. This is 40. So 40 to 1.2 right here. Please mark your points. All right, so I have 2 points. So when it was 110, it was 3.3 extension. So here is 2. If here is 2, here is 3. This is 3. This is 3. 3.24684. So 3.3 falls between 3.2 and 3.4. So it's in between this line. So I have 110 as a load. This is 100, 104, 108, and 112. So 110 falls between 8 and 12. So come right here. Is it 100? Is it 100 right here? 104, 108, 112. So it falls between 8 and 12. So this is 2, 4. So this is our here's our point right here. I come again. This is 100, 104, 108. So it falls between 8 and 112. And yes, this is 3.2.4. So 3.34 between that. So that is our point right there. So I'm counting my load in using 4 units because here is 20, if here is 20, here is 24, 26, 20, 24, 28, 32, all right, plus 4, 36, plus 4, that's 40, plus 4, 44, plus 4, 48, plus 4, 52, plus 4, 56, plus 4, 60. So that's how we are counting the loads. Now, the next load is 160, and we have a 4.8 extension. So this is 4, this is 140, here is our 160 right here, 160. This is 4, this is 4.2468, 4.8 right here. So 160, 140, this is 160. These are 4.2468 is our point right here. Please mark your points. All right, so when it was 200, we have 6.0. So 6.6 plus 200, this is 180, yes, 200, 200. So 6.0, this is 6, mark your points. All right, we have, when it was 250, we have 7.5. Here is 6, so here should be, it should be 7. It should be 7, 7.246. So 7.5 fall between 4 and 6, and the load was 250. So here is 220. Okay, it's 220. Take it down to 7. This is 7 right here. 220, 224. 224, 228 plus 4, 252. So 254 between this and this. So take it down. 7.2, 7.4. So it falls right here. That is our point right there. Okay. Next one is 290 to 10. Here is 10. Goes up. This is 260, 260, 264. Here is 280. Okay, it's 280. This is 280. 284 plus 4. 280 plus 4. 284. Plus 4, we have 288, plus 4, we have 292. So it was, so between 288 and 292, here's our point right here at the middle. So we'll mark our point right there. You have to be very careful when doing this. You must ensure that you get your exact point. So the next one is 340 to 340 as a load. The load is 340, as you can see on the graph. When it's 340, it is 16.2. When it's 340, it is 16.2. This is 16 right here. This is 340, 16.2 right here. All right, so I have plotted this graph, or this table of values on my graph. Okay, so we finished plotting the graph. What we do next is to join the lines. As you can see, I have a straight line from 0 to 250. So let me draw the lines. From 0 to 250. You can see I have a straight line right there. I have a straight line right there from 0 to 250. All right, a straight line from 0 to 250. What next? After 250, the lines begins to bend, as you can see right here. Okay, now this point, I call this point my A. Now this here is the elastic limit. Now from this point where the line begins to bend, the the force is no longer proportional to the extension, but from 0 to A, the force and extension are proportional. So this point is called, this point where the line begins to bend is called the limit of proportionality. It's called the limit of proportionality. All right. What next? We can now find our stiffness. Let me use a different marker. Okay, so let's now find the stiffness. So as I was saying earlier, you can take your gradient or your stiffness from any point on a straight line. So let me take my gradient from point 160, take it down to, please use a ruler when doing this, take it down to 4.8, yes, 4.8, and I take it down to my 160. It's my gradient, here's my F2, which is 160, and here's my F1, which is 0. Then here is my 4.8, which is my X2, and here is my X1. So from this now, we can find the value of our gradient. So what next? I can therefore say that the gradient or the stiffness or the gradient of the force extension graph is equal to F2 minus F1 over X2 minus X1. Now my F2 in this case, my F2 goes to the y-axis, which is the force, which is 160, minus my F1 goes to the y-axis, which is 0. My X2 goes to the x-axis, here is 4.8. Remember, it is 4.8 millimeters. So we convert to meters, it gives us 0.0048. So we converted 4.8 here to meters, it becomes 0.0048. 0.0048. Minus x1. X1 is right here, which is 0. So therefore we have 160 minus 0 is 160. Divide by 0.0048 minus 0 is 0.0048. So therefore our stiffness for this graph, we'll put that in our calculator. 160 divided by 0.0048 will give us 33.3. So we have 33.3 Newton per meters. You know why? Because it's the force over extension, so it's Newton per meter. So now I've gotten my stiffness, so I can put that in the equation. So therefore, my modulus E is equal to, the stiffness is 33.3 times the length is 8.0, divided by the area is 1.327 times 10 to the minus 6. All right, So we can put that in our calculator. 333.3 times 8.0 divide by 1.327 times 10 to the minus 6. That gives us 2.009543 times 10 to the 11 Pascal. 11 Pascal. Now we can convert this to gigapascal. How do we convert this to gigapascal? I know that gigapascal is 10 to the 9, so I can move these points backwards. 1, 2, that becomes 201, all right? 201 times 10 to the minus 2 times 10 to the minus 2 times 10 to the power 11. So that gives us 201 times 10. Remember in maths, minus 2 plus 11 gives us 9. That gives us 9 Pascal. So therefore we can say that our modulus E is equal to 201 gigapascal. So that is our modulus. But it's not finished right here. We are asked to find the stress at the limit of proportionality. So the stress we know is stress is equal to the force over the area. Now, the stress at the limit of proportionality is the point on the graph where the line starts to bend. So this point right here is the limit of what? Proportionality. And the force at this point is 250. So the force at that point is 250. So therefore my stress is equal to what? 250 over the area. The area is 1.327 times 10 to the minus 6. So therefore, put that in your calculator. Our stress is 1,883,948 75.7 Pascal, 0.7 Pascal. Now, we can also convert this to a megapascal, so I can see that my stress becomes, I'll move the decimal point 6 place, becomes 1, 2, 3, 4, 5, 6, 6. So that gives us 188 points. We have 3 here, we have 9. Take 1 from 9 to 3 becomes 4, becomes 0.4 megapascal. So that is the final answer. So here is how we solve questions that relate to the force extension graph. So this is our graph, and here is the values we got using the graph. So thanks for watching using the graph.